Hi everybody, welcome back. So before the big 2-week marathon at work starts, I thought I'd do another video today for fun this weekend. And I'm going to do something a little different. I am going to do a meter video. Oh no. Yes, everybody out there has done meter videos. There's probably thousands, if not hundreds of thousands of meter videos out there on YouTube land. And everybody, either does a review of a meter or they kind of talk about how they work basically, ohms and volts and amps and diode check. Those are the four big things. Most of you can already know that. And if you don't already know that, go check out the plethora of videos on that. What I thought would be a little bit interesting, is show you a few of the meters that I have. And I want to go over some of the features you normally don't see all the time or don't talk about. The less common ones. Not every meter has all these features. And when you see some of these, it might kind of tilt you towards wanting to purchase, if you're looking for a meter, towards purchasing one particular model over another because of that feature. So I'm only going to scratch the surface today because there are many different things they've come out with multimeters, both digital and analog meters over the years. And I can only do just a few in this video. But if you like it, maybe we'll do some more down the road. So let's get started with this one. Now this is an old friend. You've seen this on a lot of my videos. This is a Fluke Model 187. And I actually had this meter, well, for many, many years, probably 25 years or more. And it was the one I carried at work for a long time. And then it eventually ended up on my bench. And I'm still using it, and I love it. I have a brand new one in the box if this ever wears out, just because of how much I like these. They don't make them anymore, unfortunately. But there are other Fluke meters that are very similar to this one. And I'm going to talk about one particular feature on this that other meters have, but not all of them do. And if you ever look at the ohms on this, see where it says ohms? There's that strange little blue letters NS, and that stands for nanosiemens. And what is that? Well, the unit of measurement Siemens, and it's also known, earlier they called it mhos, which is ohm spelled backwards, is a measurement of conductance. Conductance is the inverse of resistance. Why does it matter? Well, when you're doing some measurements and some calculations, it's a little bit easier to use conductance rather than resistance. Okay, so instead of ohms of resistance, mhos or Siemens of conductance. Now, again, if you look at old test equipment like vacuum tube testers and so forth, they use the term mhos because that's the older term, because Siemens, the old Siemens unit, was originally a measurement of resistance. It predated the ohm, before Ohm's law was a thing. And it was kind of a clunky number because it was based on columns of mercury displaced by a certain amount of energy. I'm not really sure how they did it. You can look it up, and I read about it before and promptly forgot it. But anyway, suffice it to say that it didn't fit really nice with the Ohm's law. When you have 1 volt and 1 amp into 1 ohm, you get 1 watt, and everything's all based on that single unit, and they all kind of fit together. That's really important. Well, later on, they changed that terminology, and when Ohm's law came out, they took Mr. Siemens, who is a engineer and a physicist, I believe, and to give him recognition for all of his work, they assigned his name to the measurement of electrical conductivity. So, long story short. So why does this meter have that? And what good is it? Well, really what this is good for is measuring very, very high resistances. This thing has a physical limit of I don't know, it's like 400 or 500 mega ohms, which is a lot of pretty high resistance. But when you have something that's even higher resistance than that, you get beyond the range of this meter. But because of this nanosiemens mode, it can actually read higher resistances than that. It's just that it will read it out as electrical conductance because of the way that the meter puts the signal out onto the device under test and reads it back. And in doing so, this thing can read up into the tera ohms, not giga ohms. It's very, very high resistance. It can read 0.01 of a nanosiemen. And a nanosiemen is, do the math, the scientific notation. And if you take the inverse of that, you'll see it's, 1 tera ohm or 10 tera ohms, something like that. It's really high resistance. So I'm going to demo this and show you how that works and how you can measure very, very high resistances with a meter that has that mode on it. Now, some of the Fluke 87s had that originally, I believe, the earlier models. But if you have a Model 5, like I do here, it does not have it anymore. So different models of meters have different features. And it's not just Fluke that does the nanosiemens mode. There's other ones, I believe, out there. But anyway, let's take a look at it. Okay, so you can see I have a little breadboard here, and it just has a whole big string of resistors. And these resistors, I believe, are 100 mega ohms each. So 100 million ohms each one. And they're pretty good tolerance also. They're pretty accurate. So I'm going to put the clip lead on my common probe here. And I'm going to clip it to the first resistor. And we're going to see what we can find out. Okay, so we're in ohms mode right now. And if I touch this side, it should be 0 ohms or close to it, and it is. And I check my first resistor, and it's 100 mega ohms, just like you would expect. And of course, resistors in series just add up. So the next resistor, if I have 2 of them, should be 200 mega ohms, then 300 mega ohms, then 400 mega ohms, and I'm pretty much still reading it. You can see it's jumping around, it still reads it. 500 mega ohms, 600 mega ohms, and, well, we can't read it anymore. 700, 800, 900, 1 giga ohm. So you can really only read up to 500 mega ohms on this particular meter. And that's pretty good. A lot of digital multimeters will not go that high, but these ones will. And even, some of the really high-end analog meters, there are some that'll go way up, like some of the VTVMs out there. But for all intents and purposes, that's it. Now, we could use a thing called a megger or a mega ohm meter, and those will read up that high too, but the way they do it is by applying a really high voltage. So for instance, I have a megger somewhere that'll read, it applies a 1000 volt signal, and it uses that to break down that resistance and read it. And it would be able to read up to 1 giga ohm. The problem is you're applying 1000 volts to the circuit. Some circuits don't like high voltage. So what happens if you can't put a high voltage on that and you still want to read that impedance or that high resistance? That's where this comes in. So if we switch to nanosiemens mode, now you can see it says NS for nanosiemens. And remember, conductance is the inverse of resistance. So we'll take our meter here, or our calculator, and have it handy so we can look at it. And if I go to the first resistor, it will read 10 nanosiemens. So if I take 100 million, and I take the inverse, it will show you 10 nanosiemens. And you can do the scientific notation. If I go to 2, that's going to be 5 nanosiemens. So you can see, as you equally go up, these will go down. Now you have 3.3, 2.5, 2.0. You can do the math if you want. Now this one's saying 1.67, 1.7, 1.4, 1.2, 1.1, and this should be 1.0. Yep. And 1 nanosiemens equals 1 gigaohm. So pretty crazy. So you can see I can easily measure this high resistance very accurately using that mode. And that's really what this is all about. The only thing is you just have to remember to do, that you have to take the inverse of your reading if you want to know what it is in ohms. So I hope that makes sense, and I'm sure those of you who are into this stuff have some other comments. I want to move along here, but that's in a nutshell what this does. Now the next thing I'm going to do, I think, is a source of confusion for a lot of people, and because the terms get confused with one another. This meter, if you look, has an AC voltage testing. This is the Fluke 87 Series 5. But next to it, it has this little curved line with the word LO. And what this means is low pass filter. Now don't confuse this with low Z or low impedance mode, because there is another feature of a meter that this does not have. But this is called a low pass filter. Why would you want that? Well, when you start checking AC signals, what can happen is not every signal you test is a perfect sine wave, and it's not a fundamental frequency. Some of them will have multiple frequencies. So like if you're testing a switching power supply that has, has a switching frequency of, tens of kilohertz, but you want to read a low frequency voltage, those voltages will combine and will skew your measurement. So what this does is when you select low pass filter, the low pass filter will filter any signal that is above 1 kilohertz. So why would you want to do that? Well, let's say I have a 5 volt AC signal right now, and it's actually not 60 hertz. Believe it or not, I think it is a 10 kilohertz signal. You see that? And let's say that 10 kilohertz signal was riding on top of a 60 hertz signal. This happens sometimes when you have a switching power supply or a high frequency signal that's a low frequency signal with some of the switching frequency leaking through. They combine and it will skew that voltage. Now watch what happens when I turn this on. You can see, since it's 10 kilohertz, it's above 1 kilohertz, it filters that out and doesn't look at it. And since there's no signal that's below 10 kilohertz, it basically reads 0 volts. Now, if I go over and I change this to 60 hertz, like what would be coming out of your mains, it reads it. And you can see now I have a 60 hertz signal. And the low pass filter mode does not interfere with it. So that's why you would have a low pass filter. So it's kind of handy if you're checking things like switching power supplies or variable frequency drives and things like that, where you have complex waveforms, where you have like a carrier that's a low frequency, and then you have riding on that carrier a bunch of high frequency noise. That noise will add to it, and it will actually give you a false reading of the actual low frequencies you're trying to read. So that's what that does. So not to be confused with a meter that has a low pass filter on it, is a meter with low Z mode. Now, where you'll typically see these kinds of meters is for things that you would use for industrial electrical service and so forth. This one is actually one we use at work. And the reason we use that is when you're working in an electrical cabinet that has a lot of mains voltage, like 480 3-phase, 240 volts and so forth, there's a lot of electromagnetic, there's transformers and all kinds of things, and there's all kinds of electromagnetic fields being generated by these mains frequencies. And what will happen is your meter will electromagnetically couple with all that noise in that cabinet, and it'll actually read voltages that aren't really there. Those are called ghost voltages. And that's what low Z mode is meant to deal with. Believe it or not, there is not a big difference between the AC volts mode and the low Z mode, with the exception of when you switch this on, it places a component across these leads here. And the component that it places in there is a PTC, or positive temperature coefficient thermistor. That thermistor starts out at around 2 or 3K ohms, so it's like a 2,000 or 3,000 ohm resistor that it's putting right across whatever voltage you're testing. Now, if you do the math, you put a 2,000 or a 3,000 ohm resistor across, several hundred volts, it's going to draw some fairly good current, in the hundreds of milliamps anyway, depending on the voltage. But because it's a thermistor, it immediately starts to heat up, and as it heats up, that resistance will creep up and the current will drop. And essentially, when it settles, this thing will be drawing about 2 to 3 milliamps of current through the meter. And that 2 or 3 milliamps of current doesn't really pose a big problem to the circuit you're testing, depending on what you're testing. Well, this is mainly for when you're looking for mains lines and stuff like that. But what it will do is, since you have that resistor across there, when that thing cools down, you can see it zeroes out and it gets rid of all that phantom noise. This is called phantom voltage. See how even with nothing connected, it's reading 10 millivolts. And just moving the leads close to the power cord, just sticking the leads up here will give you a reading, because it's magnetically coupling the meter to your mains line. By the way, that's how those non-contact voltage sensors work, by the way, too, by magnetic coupling. So anyway, when you turn this on, that changes this to a low impedance input and eliminates that phantom voltage. A lot of times, this one I actually took from work here, because these come in really handy when you're working on things that have like 480 and things like that, high voltage like that, AC power, because sometimes you'll read there and there'll be so much noise inside that cabinet, you really don't know if that circuit is live or not. Because you can plug these in there and the circuit will be de-energized, but there's so much noise in the cabinet, it'll actually read 50 or 100 volts in there. And it's really not 50 or 100 volts. There's 0 volts there, really. But that noise kind of fakes this out into thinking that there's that kind of voltage. All right, let's take a look. You can see right now it's already reading something. Just moving it near the outlets, see how it goes up? And then moving it away, it goes back down. And if I get closer again, it goes back up. I don't even have the leads there yet. If I plug the leads into this switched outlet here, you can see it's reading voltage that's not really there. Now, this isn't a really bad example. Sometimes it reads in the tens of volts. If I turn this on, it reads 120 volts. Turn it off, now it's reading 1.3 volts. And that's what phantom voltage is. Now, if we go to low Z mode, you can see it zeroes itself right out. And if I turn this on now, and I put this in here, it reads. If I turn this off, it immediately shows pretty much 0 volts, right? See how it zeroes out automatically? Nice. And that's the whole purpose. That's what it does. So here's a pretty interesting analog meter, and I did a review of this one. I kind of like it for how inexpensive it was. And one of the unique features on it is a feature called Dohms. Now there's two different things related to this. This meter does one thing, and there's another meter I'll talk about that I don't have, but we can talk about what it is. And it's called Dohms. And what this is it's a low ohms mode. So it's for reading really low resistances. Most analog meters, when they're at their lowest scale, aren't super accurate. But this one kind of gets around it in a different way. So if you look at your normal analog meter, for instance, one of these here, they have when you're looking at ohms, they have a ×1 mode. See that? And then ×10, ×1k. This one starts at ×10. So you can see the lower scale isn't listed there. And the reason for that is because of this Dohms mode. This is the low ohm scale. And it works kind of like a vacuum tube voltmeter. So if you look at this, this is pretty traditional. You short your probes, you zero your meter out, and now it can measure according to whatever it is. And it just works like a normal ohm meter. Let's see here. This is a 7.5K. So you can see it just barely moves there. We go up to 1 × 1K, make sure it's still zeroed. And you measure here and here. And you can see it's about 7K, 7.2K right there. But when you go to do the Dohms mode, you can see the meter deflects to the right. And I'm not shorting the probes. And you zero this out very carefully here. And now you can take very low resistance resistors. For instance, I have these 20 ohm 0.1% resistors. And if you measure them, it should read 20 ohms, and I have to put the probe into the correct port. This is a different port. And you can see right on 20 ohms just about. See that? The Dohms scale is this bottom one, so it goes right on 20 ohms. Now, look at a 14.7 ohm. And the further you go to the left, the more accurate it gets. So this is a 14.7 ohm 1%. So, and you can see it drifted a little bit. I've noticed this meter does that sometimes. Cheap meter. And 10. And if I can hold the probes on here. And you have 10, 12, 14, 16. It's just right on that 15 ohm, 14.7 ohm, right there. Then, even getting smaller, here's a 2 ohm resistor. And you can see it's right about 2 ohms. And somewhere, I have to find it, I have a 1 ohm precision resistor. And this is another like 0.1%. I think this is 1 ohm, or is it 10? 10 ohms, I'm sorry, 10 ohms. You can see right on 10 ohms, dead on. See that? So it's a lot more accurate than a really inexpensive. Now, of course, that triplet that I showed you is really accurate, pretty much, but notoriously these cheap meters are not always accurate. especially at the lower scales like that. But as you saw, this one is. We'll do a couple other things that this meter can do also that I think is kind of unique. Now, while we're at it, let's look at this other thing, which is Null Mode. And you can see there's a scale down here that has a 0 in the middle. And if I turn this little knob here, I can set that right on the 0 volt mode. Now, what is this good for? Well, if I put a positive voltage on these probes, the meter will swing to the positive side. And if I put a negative voltage, it'll swing to the negative side. So this is really handy if you're looking at, for instance, a comparator or an op-amp circuit, or if you're trying to work on a, for instance, a detector in an FM receiver. Whenever you set the detector, it's actually a null adjustment. In other words, you want when you have your carrier on, but no, you don't have any kind of modulation, you want that detector to output no signal. So it should be 0 volts. However, as you start driving, a signal through it, it'll start to deflect. You'll actually get a voltage. Well, there are adjustments in that where you actually have to set it so that it doesn't by fault put out a skewed voltage. If there's anything other than 0 volts with just the carrier, you're going to get a lot of distortion in your FM signal, when you tune it in. When you hear it in your speakers, it'll sound distorted. But you use this to null that out. Now, can you do that with a digital multimeter? Absolutely you can. Some of these even have a bar graph on them, and you can see there's a bar graph here, and you can actually set the bar graph at a reference and use it. So you can do this on some digital meters as well. Or you could just watch it go from positive to negative voltage, no big deal. But this is really nice because it's damped a little bit, so the needle doesn't flicker around on you like the digital meter will. And it's just visually, it's a lot faster to watch that needle and to make your adjustments. So let's just take a look at it. I'll get a battery here, just something simple. And I'm on the plus and minus 25 volt scale. So there's a 25 volt scale and a 5 volt scale for higher accuracy, or resolution, I should say. And if I put a voltage in one direction, you could see it swings positive. And that's 10 volts right there, 5, 10, 15, 20, 25. So it's 9 volts because it's a 9 volt battery. And if I swap the leads, it makes the meter go the other way. It's about 9 point something volts. See that? So that's what a null meter does. Now, this is a really inexpensive meter, and you can see how much it does for the price. So it's pretty cool that you got these features. Here's another meter that's really one of my favorites for analog meters. This is the Sanwa EM7000, and it also has a null mode, just like this really inexpensive Tech Power that I showed you, but it does it a little bit different. This is an FET meter. It's kind of a hybrid. It's a volt-ohm multimeter similar to these, but it also works similarly to a vacuum tube voltmeter, VTVM. And I got into some of that in another video, I believe. But if we turn this thing on, you can see it will read voltages just like anything else. I can put this on here and it'll read my 10 volts or my 9 volt battery. There's the 10 volts right there. You can see it's just below it. And just like that other one, instead of switching, this one has a separate mode where you go to null mode versus regular voltage mode. This one just has this knob, and you can rotate this for any offset you want of your meter, which I really like, because if you want to null out an offset and make the offset voltage a null point, you can do that with this, much like the old vacuum tube voltmeters used to do. And just like the Tech Power, if I go this direction, it'll read a positive going voltage. And if I go this direction, it will read a negative going voltage. See that? Very handy. So I really like that. In addition, this meter will read, it has a whole bunch of features. There's a book that comes with this. There's so many things this thing can actually do. It's very deceptive. It looks like a normal analog multimeter, but it is so much more than that. It is not exactly an ohms per volt thing. Remember how we calculated the ohms per volt? When we were in the 10 volt scale, this is 20,000 ohms per volt. So that means it puts a 200 kilo ohm load across the device under test when you're checking volts. This one is more like a VTVM. It has a fixed scale of high resistance that it'll apply there, not ohms per volt. So you can see your input can be anywhere from 2.5 to 12 mega ohms. And it's a little bit different than, it's not exactly like a VTVM because they have a fixed high impedance across the board. This one still has a sliding scale similar to your this type of meter, but it's a little bit higher, I believe, ohms. Anyway, just a couple features that this has too. So that's pretty cool. Now, while we're on the subject of this meter, there's another feature that it has that other ones do not. If you notice, you have a DC volt range, and if I put it on 10 volts and I check my 9 volt battery, it swings all the way over there to 9 volts. See that? See, there's the 10 volt scale. So it's almost to 10. So it's about 9 volts, roughly. However, the input impedance of this meter is very high. So being that it's 20,000 ohms per volt, if I'm on the 10 volt scale, 10 times 20,000 is 200,000. So it's putting basically this is going to be a 200,000 ohm or 200K resistor. So it's going to put a burden of 200K across this, which 200K, if you take 9 volts divided by 200,000, you can see it's like microamps. There's just it's not drawing any current at all from this battery. The problem with that is a battery is an electrochemical device. It uses an electrochemical reaction to produce the current and the voltage that you see. And when a battery starts to go bad, it can still read good with a meter like this. The problem is when you put a load on a battery, when a battery is starting to go flat or go bad, the voltage will drop substantially, right away. And so some meters have what's called a battery mode. And we switch it down here, like for 9 volt batteries. We can check it. And you can see the 9 volt mode is this battery here. See where it says battery check? Bad, questionable, and good. See, I'm up in the good. So this is a new battery. It's a good battery. Okay. If this were starting to go bad, what would happen is it would go into bad mode. And the reason that happens is that when you go into this mode here, there's actually a resistor in here. So let's take our ohm meter again and use our meter to measure a meter. And if I measure from here to here, you can see it's putting a 700 ohm load on there instead of 200 kilo ohms. And if I take 9 volts divided by 700 ohms, it's actually putting almost 13 milliamps of current it's drawing from this battery. So it's drawing real current, similar to what a small electronic device would do. And by putting that load on the battery, if it doesn't sag, if the voltage doesn't sag, the battery is still good. But if the voltage sags, you'll see the meter will drop into the bad mode. Now they make dedicated meters that just test batteries and nothing else. And they're very inexpensive. Here's one right here. And you can see, you can pick what type of battery. So if it's a 9-volt battery like that, you can either use the leads or you can use this handy little built-in tester. And I can go like this, and it will, if I can get in there, it will measure. There you go. It'll measure it. Makes it really hard for me to hold it in there and hold it in front of the camera, but you can see using the actual probes, it's good. It reads just like this. And on these, they'll even tell you if you have, like, there's a difference between a D cell battery and a AA and so forth. If you want to look at a AAA battery, those don't really output a whole lot of current. So you can see they have a 50 milliamp load or 50 milliamp mode for a AAA battery. And they have a 150 milliamp mode for the AA, the C, and the D. So it actually puts a real load similar to what a device would on the battery. It's very cool. This one doesn't have as many ranges as a dedicated battery tester, but it does the same thing. Now the next function, some of you may know what this is. So this is just an inexpensive meter you can get online. And any of these products from Aneng, I've been really impressed with their products. They work really well. This is a very durable meter. If you want to have one that you're just going to be beating the meters up and throwing them away, this is the one to buy, rather than going through really expensive Fluke and so forth like that, because these are really accurate and they're actually pretty durable. But it has a feature that I like called NCV, or non-contact voltage sensing. What does that do? Well, in the end of the meter, there's a little electromagnetic sensor. It's test for electromagnetic fields. And when you bring it next to an outlet, so here's our outlet. I'll zoom you in. As I bring it close to an outlet, it will beep and it will let you know that there is voltage present in those wires. As I get closer to the wire, like here where it's coming in, you can see how it gets faster, and you have 2 dashes, and when I get out here, 1 dash. So it actually can test the intensity and the presence of an AC voltage. So if you're checking for mains, it's really good. I mean, you can see that this outlet is actually live. And if you're an electrician and you want to check and see if an outlet has, is live or not, this is a great way to do it. Nothing is totally fail-safe. You always want to check it with your meter too, but this is a quick way to walk around and see if you have a hot outlet or not. So another good little feature. They make dedicated non-contact voltage sensors. It just looks like a little pen with a little tip on it, and it has a LED in it, and some of them have a little beeper as well. And they're the same thing. You just move them near a mains line, and if the line is live, it will give you the little indication. All right, so there's just a few examples of some less known features that you might see on a multimeter, whether it be an analog or digital one. And some of those might be useful to you depending on what kind of things you're testing with it. So I hope you found that helpful. If not, I hope it just spent some time here on your weekend or whatever time it is you're watching this. But anyway, until next time, I wish you all peace, joy, happiness, and good health in your lives. We'll see you again real soon, and let me know down in the comments any other things that you know about meters or some of the features that you see out there. Oh, and there was one more thing I wanted to mention. I said I was going to talk about, but I didn't. And that was the Sencor FET series multimeters. I think they were called like the FE20, FE21, and FE23 maybe. They are multimeters similar to this one up here that you see, and benchtop ones, and they have what's called a low power ohms mode. And what that does is it will actually, every meter has a voltage output. I mean, that's how it works. It applies a voltage at the probes across whatever you connect them to, and then it reads back the voltage drop through these probes across whatever it is you're testing. That's how it tests resistance. The voltage on these meters can be anywhere from 1.5 volts up to, like my triplet up there can put up to 30 volts across these terminals, and even like the meg ohm meters and so forth can put out 1,000 volts. The problem is anything over about 0.5 volt is enough to trigger solid state devices like diodes and transistor junctions. So if you're doing an in-circuit test, that can kind of get in your way, because if your meter causes a diode or a semiconductor to forward bias, you'll start reading the voltage drop across that semiconductor, not the other circuits, resistors or whatever, that are in parallel with it. So what those Sencor meters will do is they have a mode that only puts out about 80 millivolts, very, very low. So it's even lower than a germanium diode. And in doing so, it has a really high sensitivity preamp that it uses, and it reads back the voltage drop from that low voltage and calculates the ohms to display on there. So what that lets you do is you can do in-circuit testing of like resistors and things without causing a semiconductor like a diode or something to forward bias. So it's a neat little feature. I don't know why you don't see that as much anymore. Probably because some of these digital meters at the higher ranges, I don't know. But no, they actually apply pretty good voltage too. I don't know. You just don't see that very often anymore, but it was a cool thing for doing in-circuit testing. But anyway, if you know anything or have any other comments, please let me know down in the comments section. And again, we'll see you soon. Take care, everybody. Bye-bye.